Hello, class. Happy Monday. Here we go. Today's assignment, we're going to review ionization energy, take notes on ionization energy in our packet, which is the bottom of page 8 and the top of page 9. Do 2 practice problems, and then you're going to be working on page 7. Page 7 is your homework, page 7 from the packet. And then just a quick update timeline this week. We have a quiz, probably 12 to 15 questions on Wednesday. It's a quiz on Wednesday on Unit 5. And then we're looking at, unless something drastically changes, we're looking at a test, Unit 5 test on Friday. So quiz Wednesday, get you some feedback. Thursday we'll go over quiz results. So hopefully you can learn from your mistakes. Thursday will be a review day. And boom, Friday test. Wrap up the unit. All right, so here we go. Question of the day: which would have the lowest first ionization energy? Sodium, magnesium, or aluminum? So let me translate this question for you. Alright, so lowest first ionization energy. So ionization energy is the amount of energy it takes to remove an electron. So the lowest first, that means which one would it be the easiest to steal one electron from? So first ionization energy is how much energy does it take to remove one electron, the first electron. If it said the lowest second ionization energy, that would be how much energy would it take to steal a second electron. And third ionization energy, or how much energy would it take to steal a third electron, and so on. We'll talk about second and third ionization energies tomorrow in class. But today, we're going to focus strictly on the first ionization energy. The lower the number, the less energy it takes. Why? Because the easier it is to steal. Alright, so the lower the ionization energy, the easier it is to remove that electron, because that's less force that you have to overcome. It's like if your 3-year-old brother is holding on to an ice cream cone, you could take that ice cream cone from him pretty easily, right? He might cry a lot, but you can rip that out of his hand very easily because he doesn't have much force, much hold, because he's not very strong. However, you try to take an ice cream cone from your dad or uncle, they're not going to let go, right? They're going to have a much stronger grip and a much bigger force that you have to overcome, so it's going to be much harder for you to steal ice cream from your dad or uncle. Alright, so atoms are the same way. So it all comes down to the ENC, the effective nuclear charge. How strongly is the nucleus able to pull on those outer electrons? What attraction is being exerted by the nucleus on those outer electrons? The lower the ENC, the lower the force of attraction on those outer electrons, the easier it is for it to take. The other thing is distance, right? The farther away an electron is from the nucleus, the easier it is to steal. The closer the electron is to the positive nucleus, the harder it is to steal. So let's go ahead and let's take a look at our first problem here. So sodium, magnesium, or aluminum. So I strongly recommend, right, this is the periodic table unit. So that means look at the periodic table when you're working on problems. The periodic table is going to show you a lot of information based on where these elements are located. So I like to look and I like to circle or highlight the elements that I'm working with here. So I'm going to say which one of these is the easiest to steal an electron from. Oh, there's a bell, 7:47, homeroom's over. And let's look here. Oh, I got a roller up here. I got frazzled by the bell. Here we go. Sodium, all 3 of these had 3 shells of electrons. Remember, we said the period number will tell you how many rings, how many shells of electrons. So period 1 has 1 energy level, period 2 elements have 2 energy levels, period 3 elements have 3 energy levels. And then before we talk about valence electrons, sodium and everything in sodium's family has 1 valence electron. Everything in group 2 have 2 valence electrons. Everything in boron's family have 3 valence electrons. And then it comes down to ENC. So look, I drew the Bohr models for us. So here's sodium. Sodium has 11 protons and 11 electrons. And you can see here that 10 inner electrons, right? 2 in the first, 8 in the second, 1s2, 2s2, 2p6. So sodium has 10 core electrons. So if I take 11 positive charges in the nucleus, I minus the 10 core electrons, the difference is my ENC, plus 1. So what does that tell me? It tells me that sodium is pulling on its outermost electron with a very weak plus 1 ENC. And if I do the same sort of math for magnesium, magnesium has 12 protons, 12 electrons, and it still has 10 inner electrons, right? It still has 1s2, 2s2, 2p6. So 12 protons, 12 positive charges, 10 of that gets shielded, blocked by those 10 inner electrons. So only 2 of that positive 12 charge are able to reach and pull in on those outer electrons. So magnesium is pulling on those outer electrons with a +2 ENC. And remember from ChemQuest 5A, these electrons don't divvy up that +2 charge. They each feel the full +2 charge from the nucleus. And then aluminum has 13 protons, 13 electrons. It still has 10 core electrons, right? 2 in the first, 1 S2, 8 in the second, 2 S2, 2 P6, and 3 in the third, right? 3 S1 or 3 S2, 3 P1. So those 3 electrons are in the third. Those are the valence electrons. And 13 protons for aluminum minus the 10 core electrons. 13 minus 10 is +3. So each one of these outer electrons for aluminum is feeling a +3 charge. So distance is all pretty similar. All right. So the dominant factor here is the ENC, the pull from the nucleus. So which will be easier to steal from? It will be easiest to steal from sodium, right? So sodium has the lowest ionization energy. It's easiest to steal sodium's electron because sodium is holding on to it the weakest force, the lowest ENC. All right. Second question here. Which element, hydrogen, lithium, or sodium, has the lowest first ionization energy? So here's a translation. Which element would be the easiest to steal an electron from? Is it easiest to steal from hydrogen, lithium, or sodium? So in this problem, we looked at 3 elements that were in the same horizontal row, right, same period. So in this question, let's look at our periodic table. We're looking at 3 elements that are found in a group. All right, same vertical family. So these are all family members. And what do we know about family members? These all have 1 valence electron, and they all, everything in group 1 has a +1 ENC. You're like, oh my goodness, Mr. Lehman, well, what's going on here? Well, if they all have a +1 ENC, and they all have 1 valence electron, shouldn't their ionization energies all be the same? No. Distance, right? Distance is a dominant factor here. Within a family, distance that the valence electron is from the nucleus is the dominant factor. So let's look here. So look, hydrogen, 1 proton, 1 electron. Now notice there is no core electrons here. So there are no shielders, no blockers. All right, so this hydrogen's electron is going to feel the full +1 force from the nucleus. Lithium has 3 protons, but it has 2 inner electrons. And so 3 minus 2 is 1. So lithium is going to feel a +1 charge on its outer electron. And then sodium, we just saw sodium, right? Sodium, 11 protons, 10 inner electrons. 11 minus 10 is +1. So sodium is pulling on this electron with a +1 charge. So think magnets. If you have 6 identical magnets, and you put 2 magnets really close to each other, 2 a little bit farther away from each other, and then 2 more magnets even farther away from each other, and those magnets are attracting each other, it's going to be easiest to separate magnets that are farther from each other. So this negative electron is farther away from that positive charge from the nucleus, so it's going to be easier to steal it. So the farther away an electron is from the nucleus, the weaker the attraction will be. Now the attraction is still +1, right? The ENC doesn't change, it's still +1 for all 3. But it's the distance, because this electron is farther from the nucleus. It's not going to, that +1 charge isn't going to feel as strong. Alright, so it will be the easiest to steal from sodium because of the weaker charge, the weaker feel of that +1 charge because of the greater distance. So here we go, notes. If you want to turn to page, this is page 8 in your notes, the bottom of page 8. Alright, let me cover up some of this. And pause this if you're getting your notes loaded, and then unpause and come back. Alright, so here we go. Notes, C1, bottom of page 8. Ionization energy. Ionization energy is the energy needed to remove 1 electron from an atom. That should be needed. The energy needed to remove 1 electron from an atom. And I actually changed that for your notes. This is a shot from a couple years ago. I'm like, that word need, I need to fix that. So the energy required, even a fancier word, energy required to remove 1 electron from an atom. Number 2, elements that do not want to lose their electrons, and we act like electrons or atoms actually have feelings and they can control this. I like to pretend that, you know, atoms are people and they have feelings. So elements that do not want to lose their electrons have high ionization energies. So if you see an element, an atom that has a really high first ionization energy, it's not going to lose any electrons because other elements are not going to be able to remove it. It takes too much energy. Number three, elements that easily lose electrons have low ionization energies. So if you're looking at the ionization energy values for an element or multiple elements, The lower the number, the easier it is to steal. And the trend is this. The ionization energy will decrease as you go down a group, like we just saw in that second question. And that's because of distance factor. The valence electron is getting farther away from the nucleus. And then as you go left to right across the periodic table, left to right, the ionization energy is going to increase because the elements in that same period all have the same number of shells of electrons. So distance is relatively stable, the same, but the ENC is dramatically changing, right? +1, +2, +3, +4. So ENC increases from left to right. Top of the next page, here's a visual, a graphic, showing you the main group elements, showing you the ionization energies. And look, hydrogen. Hydrogen is pretty hard to remove an electron from compared to family members because hydrogen's electron is so close to the nucleus. But look, as you go down the family here, lithium, really low number here, sodium, low number, potassium, rubidium, cesium. Look how low these numbers are compared to some of the other elements, and that's why they're so reactive. And group 2 elements, their ENC is +2, and so their numbers are pretty low. Look over here at oxygen, huge number, nitrogen, huge number. Now notice some of these, it's not a perfect trend here, and this has to do with sort of like Hundrel and the way that the electrons are, and so there's a little bit more detail in this. If you ever took like an AP Chem, you could learn more about this. But generally speaking, as you go left to right across the table, the ionization energy is increasing. Look at helium. Helium is the hardest element to steal an electron from. Look at that huge ionization energy value. Neon is super hard. So look at these huge numbers for noble gases. Look at the huge numbers for 17, group 17, the halogens. And it's going to be hard. We can't really steal electrons from